Okay, this is chapter 6, transforming data models into database designs. So data models is what we talked about in chapter 5. Database designs are actual plans for making a database in a real DBMS, like MySQL or SQL Server or Oracle, right? So the purpose of this chapter is to convert that abstract data model that we made in chapter 5 into a real database where we actually have real fields with real names, with real properties, like is the thing null or not null? How many characters are in the field? And we'll have the big addition of foreign keys, right? That we need foreign keys to actually store the relationship that we've denoted with lines on the data model diagrams. And we're going to look at this in such a way that we can understand how to represent all of those different types of entities and relationships that we talked about in the previous chapter. The strong relationships, the weak entities, the subtype, supertype, the recursive, all those things are covered in this chapter. How to convert those models into actual databases. So our goal is to go from a model to a database. And generally, there are 3 steps, like any good recipe, right? Because 4 would be too many, 2 would be too few. All right, step number 1 is that we have to create tables. Now, we don't have tables in the model, it's just a model. We're going to convert every entity in our model into a table in the database. We're going to talk a lot more about some details related to this, but this is an overview so you can see the forest before we look at all the trees independently and analyze them to death. Step number 2 is we need to create relationships, which essentially boils down to creating foreign keys. So creating the foreign key and putting it in the right spot is implementing the relationship. Step 3 is we have to specify the minimum cardinality. What that means is we're going to write down the logic that represents the mandatory, optional, optional, mandatory, mandatory, mandatory relationships between the different entities on the minimum cardinality side. All right, so those are we have to at least have one or it's completely optional. All right, so now we're going to step back to step 1 and talk about creating tables and look at that in a little bit more detail. So step 1 is easy. We create a table for every entity. If we have an employee entity, we want to convert that into the employee table. You have to look very closely to see any difference between these. I'm sort of annoyed at the authors for making such a subtle difference, but maybe that just goes to show you how close a mapping this is in this simple case. What is different about those 2 diagrams? No shadow. No shadow is right. That's the difference between what he's denoting as a entity and, no, I'm serious. Yeah, that's his notation. Shadow is entity, no shadow is table. Also, the better sign perhaps is if you see actual symbols, like a little key symbol, that means it's a key. It's a primary key. We've defined it as a primary key, and we don't have that in the entity. Entity is on the left, table is on the right, and there's going to be a bunch more slides like this in the rest of this lecture, and I always do it like this. All right, we've created an entity. Now we're going to specify the keys. You know keys are important. We're going to specify primary keys. Ideally, primary keys should be short, numeric, and fixed. You remember those 3 keywords? It seemed like I put them on a test or quiz or something. Those 3 properties are very valuable to have in a primary key. If you have a candidate key that meets the criteria to be a candidate key in that it uniquely identifies the row, but it's not fixed or numeric or short, like if you're using someone's first name, last name, phone number, and address, as a composite primary key. That's a little dangerous because somebody could change their address and then they've changed their primary key, and then anything that's maybe linked to that using as a foreign key, this is going to break. You follow me? So there's a lot of reasons why that would be bad. To achieve this, we use surrogate keys. You already know this because they are short, numeric, and fixed. That's why in your database, if you've ever deleted a row and added a new row, it doesn't replace the surrogate key with the auto increment. It keeps numbering as if that missing one was still there. Do you know what I'm saying? If you delete row 5 and you already have 1 through 10, it'll keep going with 11. It won't put in a 5. Secondly, he says we should define candidate keys, where candidate keys or alternate keys are synonymous terms. And what we're doing here is showing that there are other ways, there are other fields that we could use to uniquely define the rows. And he uses this kind of goofy notation to say alternate key 1.1, which means email could be an alternate key 1, whereas in customer number in that table, if we put name and city together, that's alternate key 1, and it has 2 parts, part 1 and part 2. You see that notation, the number dot number? That's a 1 alternate key, and 2.1, that means email is another alternate key. All right, so we have converted our entities to tables. We specified keys. Next, we're going to specify column properties. And this is something that we've done when we actually made our databases in the first couple chapters. And now we're talking about it a little bit more theoretically, perhaps. The first piece is the field allowed to be null? The 2 values there are null and not null. And we usually specify this such that primary keys cannot be null, but other values probably can be. In this case, they say employee name cannot be null either. I think this makes sense. We've done this before. Secondly, we often want to specify, we will be required to specify the data type of columns. And here's an example of that. Every database has slightly different naming schemes for their data types, but they generally correlate with the same generic data types of a variable length character string, a static length character string, date, time, money, integer, decimal, those different kinds of values. Some of them, even databases, can hold just a blob of data, like binary data. Some may be able to hold spatial geographic information, like lat long, GPS information. All those would be different data types that we define on columns. This makes sense, right? Database products would also allow us to define a default value. Sometimes it makes sense to give an initial value to new cells when a row is created. In this case, he has this little document that defines for certain column names what their default value should be. None of these are that interesting to me, but they're saying things like item prefix, if the category is perishable, then you put in a P. So there's some rules that are built in, some logic that would have to be implemented in a different language in order to give those new rows that value. The most common way that I've used this personally is if you want to have a timestamp of when a row was created, you can just put like equals get date time or something close to that function. So that default value of get date time will get the current date time that row was created. That way you don't have to actually insert it in when you're working with the application, the database does it for you. The last piece of column information that we want to add are data constraints. Data constraints are limitations on data values. So we may be able to define different constraints. He subdivides data constraints into domain constraints. That means that column values must be in a given set of specific values. So if we're recording gender, then the only possible values that could go in that string are MALE and FEMALE. You follow me? When you have like a set of values that are the only values in the domain that are legal to put. Range constraints are similar, but just means we have a range of values, like numeric values. Numbers that go in this box have to be between 1900 and 2100. The other two that he points out are intra-relation constraints. So this is when column values are limited by comparison to values in other columns of the same table. There are constraints on this column because of other columns in this table. That's a little bit like that default value that we saw before, where the prefix, the item prefix was P, if item category was, what was it, perishable, that kind of thing. You can also have interrelation constraints, which just means there are limitations on the legal values that this column can take based on other tables. Referential integrity constraints would fall under this category, right? Because the foreign key has to exist in the other table, so that would be a interrelation constraint. It just means there's rules that constrain the legal values for this column, and they're based on values that are in other columns of this same table. Those would really be business logic kind of rules. You know what I'm saying? And the last piece of this first step is to verify normalization. Hopefully the data modeler did their job well and did pick out all the pieces, the different entities, and structured the data well. And in that case, you'd hope that your database would be normalized. If it's not, then you need to make it normal, right? So is it in 4NF, 4 normal form, or BCNF? And if not, make it so. And this is a picture of Codd, Dr. Codd, who invented relational algebra and all this. Okay, step 2, are you ready? We need to create relationships. And like I said, that really generally boils down to adding foreign keys to the database. We learned all those different types of entities and possible relationships last time. So in this chapter, the book goes through all those in the exact same order and shows how to convert a model that's a one-to-one strong into a database design that's one-to-one strong, and then all the other ones. So that's what we're going to do next. One-to-one strong entity relationships, how do we do that? This is pretty simple. This is that club member locker example. We actually have an option in this case. If it's a one-to-one strong, we can put the foreign key on either side and both will work. It's not as if there's a parent and a child because they're equals in this relationship. If there are some minimum cardinality restrictions, like optional to mandatory, then that would make one design preferable to the other. But for this next section, we're going to consider that everything is optional to optional because that's the simple case. This makes sense. So the difference is, well, you can put the foreign key in either one, in a one-to-one. Right. If we have a one-to-n, a one-to-many relationship between strong entities, we're going to have a foreign key. But in this case, right, there's a right place to put the foreign key. In this entity, right, here's the entity. There are many departments in a company. The company name is a foreign key in department. So we're placing the primary key of the parent in the child as a foreign key. Place the key of the parent in the child. That's how this one-to-n relationship works. How do we do many-to-many strong relationships? The problem is, you see this, where do you put the foreign key? It's kind of like they both need foreign keys because there can be many in either direction. So the solution to this problem, where do you put the foreign key, is that we have to create a third table. It's called an intersection table, and it stores data about corresponding rows from each entity, and this intersection table has the primary keys from both of the many-to-many tables, and they form a composite primary key. Each table's primary key becomes a foreign key linking back to that table. So this is the database design for that previous data model. And it's unfortunate but unavoidable that we have to create this sort of artificial table. It's not present in the model, but that's the way to implement that many-to-many relationship, where both of these are a composite primary key, and they're also foreign keys in the other table. And I think essentially what we're doing is we're creating two one-to-many relationships. Okay, so we did the strong entities. Now we're going to talk about weak entities, ID dependent being the sort of more interesting. Or we already looked at how to represent end-to-end relationships, but we also in the previous chapter talked about association relationships, multi-valued attributes, and the archetype instance type of relationships. So I wanted to show you just one example of each of those. They're generally, I think, all going to be implemented the same way with foreign keys, right? Foreign keys is how we do this. So for association relationships, this is the entity. Remember this, it's an association because price is a property that only exists when part number and company name are together, and we would implement that in a pretty standard way with both of these being primary keys and foreign keys, and price is an attribute on that kind of intersection table. In this case, it's an association table, not just an intersection table. Second type of ID-dependent entity is the multi-valued attributes. We looked at that phone contact issue. You remember where there were different company phone numbers for an individual company. So this entity would be translated into this database design. And lastly, for the archetype instance kind of relationship, an entity like this where we have classes and sections, and a section is like an instance of a class. Class can exist without a section. Section can't really exist without a class. It's going to look like this, and that class name is going to be kind of a foreign key. The class name, section number together are a primary key for the section table. And I think the last type that I want to talk about is this subtype relationships. We looked at these, what to me feel like very object-oriented inheritance kind of relationships where we have students, and there can be undergraduate students or graduate students that have a set of properties in common with student, and we can implement these using tables, a table like this, where student ID is a primary key for undergraduate, but also a foreign key to a row in this table. And likewise with graduate, student ID is a primary key for the graduate table and also a foreign key in the student table. All right, so that's step 2, creating relationships, which involves generally making a lot of foreign keys and having those constraints on them. All right, the last piece is, in my opinion, the ugliest and the messiest, which is designing for minimum cardinality. So you remember that we talked about the optional, that is parent to child, minimum cardinalities, the mandatory, optional, mandatory, and mandatory. So those are the 4 options that we have. And what the authors of the book do is they first show you a set of actions that are required in order to enforce minimum cardinality on different events. So for an update event or an insert event or delete event, this is what needs to happen in the parent or the child to enforce an MO type of minimum cardinality, or an OM, or an MM. So I'm about to show you a table, and this table encapsulates, it summarizes what actions need to be taken or may be taken when a parent is required. So these are the parent actions. So if a parent is required, that means it's a mandatory. On insert, this is what we do to the parent, this is what we do on the child. Does it make sense how to read this table? So depending on your policy, you could do either one, but you'd have to do one of the 2 in order to be safe, to actually implement the minimum cardinality. Does that make sense? This is the counterpart to that table, which is the actions that we should take when a child is required. So when we insert, the parent would have to get a child, the child would have to do anything. If we modify the key or the foreign key, we have to update the foreign key of the child. If it's not the last child, it's okay. This is ugly over here, if not the last child, because you have to search the database to figure that out. All right, one more table to try to put this all together. All right, so keeping those other 2 tables in mind, this table shows which of those actions need to occur in different situations. So if we're doing an optional minimum cardinality relationship, then we don't have to do anything, which is nice. And that's what we assumed for all of the previous, like all that step 2, step 1 stuff. If it's mandatory optional, which means the parent is mandatory and the child is optional, then you have to do all the parent required actions, that first table that I showed you. You'd have to follow those when those events happen to make sure that you've continued to enforce the minimum cardinality requirements, to make sure that we still have, right, that the parent is required. On the OM, that's the reverse. And in that case, we would do everything that's in the previous table with the child required actions. For the mandatory optional, those are fairly easily enforced by the DBMS by defining referential integrity constraints and making the foreign key not null. However, when you go optional to mandatory, where the child is mandatory, those are difficult to enforce. And in order to implement that logic, you have to run code on certain events, and those events will be, well, you'll have to do it in what's called a trigger, where the triggers are, it was on the quiz, right? The triggers are sort of, it's either application code or it's stored procedures in the database, the DBMS, that run at certain events. OO is super easy, MO is pretty easy, OM is hard, and MM is really hard. Because MM is the worst possible combination. You have to do both, and the authors say this requires a combination of complex triggers, and the triggers can lock each other out, and you really have to think about what you're doing carefully to do that correctly. So it's a pain if you have those mandatory restrictions. Just so you'll have it in your notes, what are triggers? Triggers are these stored programs that are executed by the DBMS whenever a specific event occurs. So they're very event generated. And as we said, they're used to enforce specific minimum cardinality enforcement actions that can't otherwise be programmed into the DBMS. When you have these more complex logic that has to be followed to make sure that you keep your minimums. And these would be DBMS specific code. That code wouldn't necessarily translate from one database to another database. All right. So to sum this up, in this chapter we have looked at transforming data models into database designs, and our goal in all this was simply to convert that abstraction into a reality, like a boss, as always, right? We want to convert that data model that has a shadow into one that does not have a shadow. And the one that doesn't have a shadow is better, not just because it doesn't have a shadow, but because it's closer to reality. It's implementable. So we can actually store the data that we'd like to store.